Okay, hi physics people, we are on to particles, and there's not really any alternative to learning lots of vocabulary and what it all means. So if I was to say to you, I've got a list of particles here that I've just come up with, and I've got over here a list of groups that I want to put them in. If you're not happy what these words mean, then you simply can't allocate them to groups confidently, and you really can't access the whole program. So if you can't say to me, I know that neutrinos and muons are leptons, and they're going to go into the lepton category, and my electron is also a lepton, and a proton, not sure what's that. Now pion, that's a meson, so that's going to go over there. You need to know what these different categories are. To some extent it's a bit confusing where they've come from the Greek words, but you need to learn it in any case. So let's just move on to the next section. What does the word fundamental mean? Now, if something is fundamental, you simply cannot split it up into smaller particles. Now, history suggests that we don't always know exactly what's fundamental at any stage, and as time moves on we might make new decisions, but for the time being, particles that are not made up of other particles we call fundamental. So an electron, there's nothing else in an electron, so it's fundamental, whereas a proton is made up of 3 quarks, so a proton must not be fundamental, but a quark is fundamental. And an electron neutrino is also a fundamental particle. So, now, let's move on to the whole standard model business. Now, the standard model that you're familiar with, that we've discussed, is made up of several key elements, but to keep it simple, let's do it in sections. We've got the quarks. Now the quarks were originally when Murray Gell-Mann and I forgot the name of the other guy, were thinking of quarks. They only knew of 3. They only knew of up, down and strange, but now we consider there to be generations of quarks. So really, the first generation was the up and the down quark. And most of the stuff around us is made of those. And the other more massive quarks, we don't really deal with in terms of they're generally generated in high energy experiments. Now, along with the quarks, we also have the leptons. And we've got our first generation. You could think of it as essentially a first generation, an electron and an electron neutrino. And then a second generation, kind of like a kind of heavier version, and an even heavier version, or an even more energetic, an even heavier version. So we've got most of our matter that we deal with is going to be basically made up of these particles, but this is the complete set, so far as we're aware. Now, we've also got the particles that we use as exchange particles to carry the forces. So over here, we've got the gluon, the photon, and the Z and W bosons. So these are all called bosons because they carry forces. And of course, the gluon carries the strong force, the photon carries the electromagnetic forces, and the weak force has these the Z and W bosons. So you've got to know that, whereas I've just written it in symbols. You really need to be able to say, this is up, down, etc. You need to memorize that. And there is quite a good Glasgow physics video for that. So, other ways of thinking about it and ways of working it. Well, you could decide to sort it by forces at the starting point and say, okay, what's the question here? Do you feel the strong force? So, if you feel the strong force, if you answer yes to that, then you must be a hadron, which means you're essentially made up of quarks. All hadrons are made up of quarks. And so, over here we've got you're either a baryon, which means you're made up of 3 quarks, or you're a meson, which you're made up of, well, I was going to say 2 quarks, but to be more precise, it should be a quark and 1 antiquark. So, really, that I've written 2, but really it should be 2 goes to 1 quark and 1 antiquark. Now, leptons do not feel the strong force. So you've got all the leptons there, electron, muon, tauon, and their neutrinos. And of course, the neutrinos are interesting because they feel the weak force. And the one thing for higher, you think they feel the weak force, and they are important and observed in beta radiation. So you think beta radioactive decay, perhaps would be a better way of put it. So you think, yeah, weak force, evidence of that is seen in the beta radioactive decay. Right, now, what else did we have in mind for this? Now I've got essentially a restatement of that earlier point there, that the hadrons and mesons, hadrons being split into baryons and mesons, 3 quarks, 2 quarks, 1 quark, 1 antiquark. Okay, so really, I think you should make a good effort to learn what all these words mean, what the groups are, and everything. And I will set you past paper questions as Google Forms to keep you tested on that. You should also, realistically, be on Memrise. No one in the group has been on Memrise. I've been on Memrise just to check and do all my personal memory training. So let's see some action on Memrise if you want to be successful in this sector. Now, in this video, I also want to go on to move on to the more mathematical aspects of this, because there's almost no maths in the actual particles. It's more narrative based. And say, okay, let's talk about electric fields. What is an electric field? Now, don't want any jokes. An electric field is an area in which a charged particle experiences a force. So this is our general field definition. A magnetic field is an area in which a magnetic material experiences a force. So, well, also charged particles, if they're moving, will experience a force in a magnetic field. But the point I'm making is the general field idea in physics is a field is an area in which something will experience a force. A gravitational field is an area in which an object with mass will experience a force. So some aspect of this, of what I've said, is a general definition of what field is in physics. And so a field is an area in which something experiences a force. A gravitational field would be a massive particle would experience a force. Okay, so let's have a look at this. How do we draw electric fields? Now, in some respects, this is again true for all fields, but we start off by imagining the force on a small positive test charge. Now, when I say imagine, we could also calculate it, but for the purposes of higher, we're just going to imagine and not do a lot of calculations on fields. So we've got a small positive test charge, and we're going to move that test charge around the field, mapping the force on the positive test charge at different places. And it's definitely not a whole coulomb. I made a mistake there. So let's have a look at how that works. So if I've got a negative charge here, and I am just I put a small positive test charge nearby that negative charge to see what effect it has. I can just move that one around. So I'll say, okay, I'll put my small positive charge over here, and then maybe I'll find it's got a force towards the negative charge. I could put my positive charge here, it would have a force towards the negative charge. I could put it up there, it would have a force towards. Put it up here, it would have a force towards. So wherever I put it, it will have a force towards. And if I joined up all those little vectors, I could make a field line. And so if I put it here, it would be directly towards. So you end up with this field line system, which is a bit like the spokes of a wheel. And so we call it a radial field. And the direction is important because our definition of electric fields is based on using a small positive test charge to define the field. That means that we get something like that. Now, in getting to this, I think I've missed so in the same way, so you notice here for a negative charge, all the field lines are radial and going into the charge. In the same way, if I were to look for a positive charge, then in exactly the same way, all the positive charges small positive charges that I put near it would experience a force away. So I'd end up with another radial field pattern in which, So a point charge, perhaps should have said this in, if you have a single point charge, you get a radial pattern. Okay, and if it's positive charge, then the field lines will be pointing away because like charges repel. And if it's a negative charge, the field lines will be towards because unlike charges attract. So if I then arrange my charges in lines, as I have done here, I can make a different kind of field that's called a uniform field, not a... So if I put the point charge here, it's going to experience some sort of repulsion from these positive charges and an attraction to these negative charges. So it's going to generally go that way. And if I were to put it here, of course, it would generally go that way. If I put it here, it would still go that way. Here, that way. At the ends, it might be pushed a little bit away and a bit towards. So at the end here, it might be like more commanded by the away from there. And here it might be more commanded. So you can get a kind of curvature around the end. Yes. But generally speaking, with this system, you get uniform fields. And these, of course, are the ones we use to accelerate particles, uniform fields. So we might get something like this. So here's my uniform field. And that's the name for it. And to get a uniform field, I have to have my charges arranged in lines. And of course, I don't arrange charges in lines. The way I do this is by connecting some sort of power supply to push these charges around. So take the electrons off one plate and push the electrons around to another plate. And if I can do that with a great energy, then I'll be using a high voltage. Because of course, from our definitions we've talked of on electromagnetic EMFs, voltage is energy per coulomb of charge. So, to finish off for our charge, the last step really is to look at how do we actually do this. Well, we have some sort of power supply. Now I often use a 6,000 volt power supply that you've seen, and we'll have some sort of particle here. And let's say, for the sake of argument now, if this is connected to the plus side of the power supply, then this is essentially my positively charged plate. And this is my negatively charged plate. So if I magically put a proton in here. Now, for the purposes of this experiment, I've got to do this inside the huge sort of glass light bulb effect so that I can actually keep out all other air particles. So this has to be in a vacuum. So I don't want to forget that this has got to be in a super low pressure place where there's not going to be anything for this proton to bump into. So it can then fly across and it's going to gain energy. And the energy it gains from this field, because it's going to be pushed by the repulsion from this positively charged plate and attracted to this negatively charged plate, the energy that's gained is going to be the charge times the voltage. So the EW, the energy gained, is the work done by the electric field on the particle. The particle is gaining energy, it's gaining kinetic energy. Okay, now for a proton, the charge is equal to the charge on the electron, E, which is the fundamental constant. So in the same way that c is the speed of light, little e is the charge on the electron, which is 1.6 times 10 to the minus 19 coulombs. So I can easily work out my work done. It's going to be the charge times the voltage, not a huge voltage. And so it seems like a small amount of energy. Now, if you were to compare that to the energy in half a can of beans at 682 kilojoules, then this looks small. Half a can of beans is very similar to the entire energy in a 355 ml can of Red Bull. That's a lot of energy. So this seems like a really small amount of energy. Okay, and I was thinking that. Are you going to think, this is a really small amount of energy, what's he talking about? So this clearly is a very small amount of energy if you compare it to any meaningful amount of food. But that is a completely silly comparison because all that energy has been transferred to a particle whose mass is only 1.67 times 10 to the minus 27 kilograms. A very, very small thing. So if we sort of have a look at that and say, okay then, the kinetic energy of that particle, assuming it started from rest, which you might find some questions in which it doesn't start from rest, but is the gaining kinetic energy of this particle is certainly going to be the work done by the field. So let's have a look at that. The charge times the voltage is going to, that's my EW, and that's going to equal the standard kinetic energy equation. So there's my equations that I've now put equal to each other. If I substitute in on the old trick of substituting in everything I know in case there's a mark for substituting before I do my clever algebra, then have a bit of a rearrange. Then I need to square root that to get my V, and having square rooted, I get 6.910. So this is actually going quite fast. So that's pretty fast, but if I was doing it with an electron and up the voltage to 6,000 volts, I'd get something significantly faster. So what I'd like you to do is go to page 97 and 98 of the blue book and work through all the questions to try and understand, practice using this routine. And remember that I also want you back on Memrise, learning what the words mean. Okay.